Right now, somewhere in the North Atlantic, a container ship the length of 4 football fields is moving at 15 knots through water the temperature of a refrigerator, below the waterline, in the dark, in the cold. In the relentless pressure, something is happening that its crew cannot see, cannot stop, and cannot ignore. A city is growing on its hull, not rust, not barnacles. A living city. Bacteria, algae, tube worms, mussels, bryozoans, entire ecosystems colonizing every inch of submerged steel, multiplying in real time, adding weight and drag so steadily that by the end of a single voyage, that ship is burning 8% more fuel than it did when it left port. Over a year, that number can climb past 40%. Over a decade, unchecked, a ship can become so encrusted that it moves like a building being pushed through water. The obvious answer is maintenance. Scrape the hull, clean it, keep it smooth. And yes, the shipping industry does that. But the real answer, the one that has driven engineers, chemists, naval architects, and regulators into decades of conflict, is paint. Specifically, a very particular shade of red. Most people who notice the red hulls of large ships assume it is tradition, a nautical aesthetic, maybe iron oxide, the natural color of rust prevention primer, just left visible. Some assume it is simply a marking system, different colors for different companies or purposes. All of those assumptions are wrong. Or rather, they are the surface of something much deeper. Because that red paint is not decorative, not traditional, and not arbitrary. It is one of the most consequential chemical technologies in the history of global trade. And right now, the entire industry is scrambling to replace it, because the thing that makes it work is also slowly poisoning the ocean floor. By the end of this, you will understand why that particular color exists, what it is actually doing to the water around every ship on Earth, and why solving this one problem might determine whether global shipping can survive the next century. The first explanation most people reach for is drag reduction. Smoother hull, faster ship, less fuel burned. That is true to a point. A clean, smooth hull does move through water more efficiently than a rough one. Naval architects have known this since the age of sail. There is real science behind it, but drag reduction alone does not explain why ships are painted at all, or why that paint has to be chemically active. You could paint a hull with ordinary paint, any smooth coating, and you would reduce drag just fine. The shipping industry did not spend billions of dollars and 100 years of chemistry research on ordinary paint. Something else is driving this. The second explanation is corrosion. Seawater is extraordinarily corrosive. A bare steel hull, unprotected, will rust through within years. So paint as a protective barrier, and again, this is real. Anti-corrosion primers are a critical layer in any hull coating system. But corrosion protection explains the primer layer, not the active outer coating. The red layer is not there to stop rust. It is there to stop life. The third explanation, the one that gets closest to the truth, without quite reaching it, is biofouling prevention. Marine growth on a hull increases drag, increases fuel consumption, and causes enormous problems. Sailors and ship owners have known this for centuries. The ancient Greeks reportedly coated their warship hulls with tar and arsenic to keep growth at bay. So, the paint is a biocide, a substance that kills marine organisms before they can attach. That is the explanation that most people stop at, and it is correct. But it leaves the most important question completely unanswered. How? What is actually in that paint? How does it work? Why has it proven so difficult to replace? And what does it do to everything else in the ocean when it does its job? Here is where the story gets strange. For most of the 20th century, the most effective anti-fouling paint ever developed contained a single active ingredient, tributyltin, known as TBT. It was first introduced commercially in the 1960s, and it worked better than anything that had come before. Ships coated with TBT-based paint stayed clean for years. Fouling rates dropped dramatically. Fuel efficiency improved across the global fleet. By the 1980s, nearly every major shipping company in the world was using it. TBT is an organotin compound, a molecule built around a tin atom, bonded to 3 butyl groups. What makes it so lethal to marine organisms is the same thing that makes it effective as a biocide. It is extraordinarily toxic at incredibly low concentrations, parts per trillion. A concentration so small that a single gram of TBT dissolved in an Olympic swimming pool would be enough to disrupt the reproductive systems of oysters. Think about that scale for a moment. Not parts per million, not parts per billion, parts per trillion, and it still works. The mechanism is brutal in its simplicity. TBT is lipophilic, meaning it binds to fats. It penetrates the cell membranes of marine organisms, disrupts their mitochondrial function, interferes with hormone signaling, and causes imposex, a condition where female mollusks begin developing male reproductive organs. An oyster bed near a busy harbor. Throughout the 1970s and 1980s was not just struggling, it was being chemically rewritten. Scientists first noticed something was wrong in the English Channel in the late 1970s. Oyster populations near ports and marinas began collapsing. The shells were thickening abnormally, a physiological stress response. Dogwecks, small, predatory sea snails, were developing imposex at rates approaching 100% in some areas. Then researchers connected the pattern to TBT, and a slow, grinding regulatory battle began. France banned TBT on vessels under 25 meters in 1982. The UK followed. The United States acted in 1988. But ocean-going vessels, the massive cargo ships, tankers, and container ships that move 90% of global trade, were exempt. The argument was that the paint was applied in international waters and regulated by international law, not national governments. And so the International Maritime Organization, the United Nations body that governs global shipping, spent the next 15 years in negotiations. The global ban on TBT finally came into force in 2008. By then, the damage to coastal ecosystems around major ports was extensive and, in some cases, irreversible. This is where the red paint becomes interesting again, because the replacement technology, the system that nearly every ship in the world now uses, did not just change the active ingredient. It changed the fundamental philosophy of how antifouling paint works. The dominant system today is called a self-polishing copolymer. It sounds technical, but the concept is elegant. Imagine you are trying to protect a surface from organisms that want to grow on it. One approach is to paint on a biocide and hope it slowly leaches out over time. That was the old approach, and it worked until the paint layer became exhausted or irregular, exposing some areas while oversaturating others. The self-polishing approach is different. The paint itself is designed to erode. At a controlled, predictable rate, the outermost layer of the coating dissolves as the ship moves through water. As it dissolves, it releases biocide, usually copper compounds, sometimes combined with organic booster biocides in a consistent metered dose. And as one layer goes, it exposes a fresh layer beneath, which will begin polishing itself in turn. The ship, in effect, is always wearing a new coat of paint. It maintains its smooth profile and its biocidal activity simultaneously. For 5 years or more between dry dock intervals, the red color comes from the copper. Cuprous oxide, the primary biocide in most modern antifouling paint, is a deep brick red. It is the color of old copper roofing, of oxidized pennies, of terracotta tile. When you see the waterline of a large vessel and notice that distinctive red-orange band along the hull, you are seeing copper oxide, and you are seeing a chemical reaction happening in real time, designed to be lethal to everything that tries to settle on that surface. But here's the question the industry has been sitting with for more than a decade. Copper is not harmless either. Copper is a natural element, and at low concentrations, it is essential for life, including marine life. But the concentrations around busy ports and anchorages have been climbing for years. The San Diego Bay in California has been the subject of ongoing study, and researchers there have found copper concentrations in some areas that exceed chronic toxicity thresholds for sensitive species. Similar findings have been documented in marinas throughout Europe, Australia, and Japan. The environmental pressure is building from 2 directions at once. Regulators in several jurisdictions, California, Denmark, and the Netherlands among them, have already moved to restrict or ban copper-based antifouling paints for recreational vessels. Commercial shipping is still largely exempt. For the same structural reason that protected TBT for decades, the ships operate in international waters. And the regulatory mechanisms are slow, but the shipping companies themselves are beginning to move, not entirely out of environmental conscience, but because of economics. The cost of bunker fuel, the heavy oil that powers most ocean-going vessels, is one of the largest operating expenses in the industry. And the pressure to reduce carbon emissions is now backed by hard regulations from the IMO, which has set mandatory efficiency targets for the global fleet. A fouled hull is an inefficient hull. An inefficient hull burns more fuel. Fuel costs money and produces carbon. The math is merciless. What this means in practice is that the next generation of anti-fouling technology is a race between three very different approaches, and the outcome will determine the environmental footprint of everything you buy that has crossed an ocean. The first approach is non-stick coatings. Silicon-based surfaces so smooth and so slippery that organisms cannot get a grip. No biocide at all. The drag reduction these coatings offer is measurable and real. Their limitation is that they are passive. They work best when a ship is moving fast, but in harbor, at anchor, or in slow transit through coastal waters. Organisms can establish themselves and are not washed away. Once a biofouling community gets started, even silicone cannot stop it from growing. The second approach is mechanical underwater cleaning robots, remotely operated vehicles that scrub a hull while the ship is in port. Several companies are now operating these systems commercially. They reduce the need for biocidal paint substantially. The problem is cost, logistics, and coverage. Not every port has the infrastructure, and a robot cannot clean every surface with equal reliability. The third approach is biological developing coatings that mimic the surface chemistry of organisms that naturally resist fouling. Shark skin, lotus leaves, and the surfaces of certain marine invertebrates have evolved extraordinary resistance to colonization. Researchers are attempting to replicate these surface structures at the nanoscale. Some of this work is genuinely promising. None of it is ready for commercial deployment at scale. What this means for you, right now, is this. Every container that crosses an ocean, every phone, every shirt, every piece of furniture, every gram of coffee arrives with a carbon and chemical cost embedded in the paint on the ship's hull. And the industry that carries 90% of global trade is quietly in the middle of one of the largest materials science transitions in its history, driven by the same pressure that drove the TBT ban. Growing evidence that what makes ships efficient is making the oceans sick. There is one more layer to this story that almost nobody talks about. When ships travel internationally, they carry more than cargo. They carry organisms, not in the hull paint under it and on it, in the crevices that no coating fully protects. Invasive species transported in ballast water have already rewritten marine ecosystems in the Great Lakes, the Black Sea, and San Francisco Bay. The zebra mussel, the Chinese mitten crab, the European green crab, all of them arrived in the ballast tanks, or on the hulls of ships. The antifouling paint that is trying to prevent fouling is also imperfectly functioning as the last line of defense against species transfer between ocean basins. If the industry moves to purely unchecked, non-biocidal coatings before the biological and mechanical solutions are truly ready, it opens a window for ecological transfer on a scale that is difficult to predict and nearly impossible to undo. So the next time you see a ship in harbor, that vast red hull rising out of the water like a moving cliff face, you are looking at a chemical and ecological negotiation that has been running for more than a century. A negotiation between efficiency and toxicity, between trade and biology, between keeping ships clean and keeping the ocean alive. The paint is doing something. The question we have not finished answering is, at what cost? That question connects to a much larger system, the one governing how every massive industry that touches the ocean is being forced, slowly and imperfectly, to reckon with what it is actually doing to the water. We will be coming back to that system, because the ships are just one piece of it. If that is the kind of thinking that keeps you up at night, the hidden mechanisms behind things that seem ordinary, this channel exists for you. Subscribe, we keep digging.